Hi, today I would like to welcome you to a tutorial video to show you how to process LiDAR data from the Qube 240 with Applanix POSPac and the CloudStation software. Before we start working with the CloudStation software, and especially when you start the CloudStation software for the first time, I would like you to check for the settings. In the upper left corner, you can open the settings and you can switch between these windows here. The first one, the general, is to enable mouse wrapping. Then you can allow the network settings, and of course you can set your preferred language. The second one is for the license. So of course you need to activate your license. For this computer the license is already activated, and when you receive your Qube 240 and the software, you will find a document explaining to you exactly how to activate the license. Next here there is the browser for the right LiDAR calibration file. So every single Qube 240 comes with its own LiDAR calibration file, which is actually named like the serial number of your LiDAR. And you have to use this file and to browse for the file and put it here into the CloudStation to use the right calibration values for the bore side angles. Then we have another one for extraction. Here you can set the minimum laser range, for example 20 meters. This is especially useful very close to the UAV. You might hit some dust in the air or some objects like insects or birds, and that might create some artificial points in the air. And to prevent that, you can set a minimum distance of 20 meters. That means all points closer than 20 meters to the UAV will be deleted automatically. Last not least, there is a system setting, and I would recommend to enable your better graphic card. For example, here I activated the GeForce RTX 2070 for OpenCL processing. Once the settings are done, before we start opening the project, I would like to show you the data which we are using today. So we are using today 3 files which comes from the Qube 240. From the USB stick there's a YellowScan file, a TO4 file which we will later use with the POSPac software, and there's a LiBox file. And of course there are a couple of Rinex files, especially the O files and the N files are needed to do the post-processing. Of course we could now open the raw data directly with CloudStation, but then the data would not be post-processed. Therefore I minimize the CloudStation window for a moment and I open the POSPac software, and I would like to show you how to use the POSPac software to do a first PPK processing of your 3D trajectory. Once the software is open, or once the software is ready, we start by clicking on New Project, and we just use a template and an empty project will be created. Here on the left side you can see Mission 1 is our empty project. Next we click the Import button, and we will have to specify the path to find our data. The data for this tutorial is on my SD drive, and I called it Flight 3 Tutorial, and in the Flight 3 Tutorial folder we should see a couple of files. Alright, now we have to go in a subfolder. There's a YellowScan subfolder in the tutorial file, and then we can see all the files. So again, here's the LiBox file, the TO4 file, the YellowScan file, and a couple of Rinex files. First of all, we load the TO4 file by importing the TO4 file, and then some processes are running in the background, which you just monitor and watch. So there some checks are going on, the IMU data is checked, and then the software is checking for GPS ephemeриdes from Trimble and some other companies. Some are available, others not, and it will automatically download the right data needed. So no action required, we just watch. And these windows will close automatically after processing. Okay, this is the flight path of the drone. So here we have the takeoff. We are flying to the calibration pattern, and then towards the first waypoint, and then left, right, all the runs, and at the end it's flying back to the landing location. So next what we need to do is we will have to load the RINEX files. So we again activate the mission tab here. We click import, and we now select all the O files, which are the RINEX files, and we import. Okay, once this is done, we have to open the mission on the left side, and we search for the base station, and we open the base station, and we do a right click on the base station. Here on the Alpha Kilo 1, we do a right click and we go to the coordinate manager. This is important to set up the right coordinate system for the base station. So now here, assuming you are using a RINEX file from an official base station like a Trimble, Leica, Topcon, whatever base station, the station information should be accurate enough and there's no need to change the coordinates. For the case you have been using the iBase and you know the exact position of the iBase, you can switch to decimal degrees and you can change the coordinates, the latitude and the longitude and the altitude to the correct values. This is quite important to make the absolute accuracy right. If you would not do this, the relative accuracy would still be okay, but there might be a shift of 50 centimeters or even a meter in any direction because the iBase can't measure its own position with an RTK or a PPK accuracy. But this data set is from an official Trimble base station, so we don't change the latitude and longitude. We just check for the frame. Even the antenna information is correct, so we check for the frame information. Preset is the ITRF00, and for this specific location we would change it to ITRF 2014. And the epoch for the position of the base station is the 1st January of 2010, ellipsoid WGS84. Once we are happy with all the settings, we apply the changes and we close the window again. So finally, we do another right click on the base station here on the left side, and we set this to be a base station. So set base station, we press this, and now it's calculating the accuracy for this RINEX file and the overlap with the TO4 file. So then after this process we will directly see whether we have a 100% fixed solution or a 90% fixed solution and 10% float solution. This is the result of this process. So 99.17% fix and 0.83% float. That's pretty good. And we close the window by clicking OK. So this is the moment I would recommend to save the project, just in case the software is crashing or something is happening, to not necessarily do the steps again. So I save this to the same directory. Let's just go to Flight 3 tutorial and I call it POSPac Flight 3. So now we could jump into this step directly if there would be an issue. And now the final step to process the The PPK trajectory is we click on the GNSS inertial processor and we just click run. So this will now take a moment. While this is doing the processing, you can monitor the accuracy here, and there are some results displayed on the right side. And actually what we can expect is a 1 centimeter, 2 centimeter, 3 centimeter PPK average accuracy. And once the process is completed, the last step is to export the SBAT file, a text file which we will later need in the CloudStation software. So processing is done. We can now see that there's a second trajectory which is displayed in a green color and a magenta color. So the processed one is the magenta color now, and we can also see the baseline distance between the takeoff point and the base station. So last step, tools. Export. We are here already in the right format. We would like to export an ASCII file, all records, ellipsoid height, only the post-processed coordinate output in meters, let long in degree decimal, and finally we just have here to specify the right file name. I would recommend to put it in the same folder where all the other raw data is located. And what I usually do is I call it SBAT3, for example here SBAT3, to immediately understand it's the SBAT file for the third flight. And we just click on save. And finally, don't forget, this is just specifying the name. Finally, you will have to click on export, which is actually doing the export. If you miss this step, there will be no file in your directory. Export, so now the SBAT file is actually written. And then we are done with POSPac, quite straightforward and easy. And then we are ready to process the data with YellowScan CloudStation software. So now we are back to YellowScan CloudStation, and first step is to open the project. Well, we are in the right directory flight, free tutorial, YellowScan folder, and we open the YellowScan file. And then we should immediately see the runs. So these are the runs which are automatically detected. We can of course modify them, or we can delete all of them and create our own runs. To create our own runs, we just select a run by clicking on it, and it will suggest a length, and we can modify this slightly by moving the slider on the lower part of the screen to make it straight, and we would not like to process the data in the turns. So let me just for today select 3 runs, 1, then 2, this is the second one, and okay, and the third one. Okay, we have 3 runs. I'm not processing all of them just to save time in this tutorial. And well, now I'm happy with these runs, and now we check the settings. We have this is our YellowScan file. The PPK solution is already correct. It's the SBAT3 file, the one we processed with the POSPac. The set reference is the POSPac elevation, so it's ellipsoid height, and we have the right calibration file. We are using the full field of view, minus 35 degrees left to plus 35 degrees to the right, and so we can start the processing by hitting the play button. So the raw data processing is done. We can, with the mouse wheel, we can zoom in and out to this point cloud. We can hide the 3D trajectory here with the show trajectory button. So let me hide this because this information is not relevant anymore. We have here in the top, we have a wheel where we can press to the west view, to the east, or to the north. So we can change the field of view, and we can of course use the mouse to rotate the point cloud and to move the point cloud. Yeah. Now I'm rotating it and I'm zooming in, and I can move it, and we can here see the road, and we can zoom in here to the road structure. And yeah, there are some more nice tools here on the left side. There is an EDL, which is a kind of a shading effect. You can enable and disable. I usually like this effect, and you can make this effect more harder and softer. So actually this is up to you whether you want to see more terrain details or less terrain details in this first quality check. You can change the point size from small points to large points, depending on the view distance. And we can colorize the point cloud by many different parameters. So for example, the echo, where we can change between the first, second and third echo. So we can here only look at the second and third echo, or only at the first and third, first and second, and so on. We can look to the maximum echoes. We can check for the classification if it's already done, not yet. We can look for the stripes, so we nicely see the overlap of the data. We can check for the intensity values. These are the intensity values of the LiDAR. So even if you would fly the LiDAR at night, you would see the texture, and you can use this slider here to do a contrast stretch to see much more details. For example, here in this open area, you can see some darker areas, probably a result of driving cars, and here brighter areas. The brighter the area, the more reflective. The darker the area, the less reflective the LiDAR signal or the surface. So this is a nice tool to check the data quality. We can also colorize by scan angle and by GPS time. If we select the elevation, you can also use this slider to change the color ramp in the lower part, in the blue part, and in the red part here on the right side. Okay, so that's pretty all you can do at this stage. The next step would be to process the strip adjustment. Therefore, we should click here on SA, like strip adjustment. And there are two methods for the strip adjustment. There's a robust method, which is quicker, and a precise one, which is slower but more precise. And the precise one is especially the right one for the Trinity, because we are flying very long runs, and especially on long runs with an IMU drift, the precise method is the one which is recommended to improve the alignment of the point cloud in the overlapping area, especially for the long runs. For those who want to use ground control points at this stage, you can check this box, use ground control points, and you can load ground control points in UTM and ellipsoidal height. And these ground points will also be used to anchor the point cloud and adjust the point cloud to make the match better and the final result a bit better. I rarely use this option, especially because of the reason that I usually can't provide ground control points. For example, for this data, there was no chance putting ground control points in most parts of the area because it was populated by vegetation. So precise, and then we just hit the process button, and this will approximately take as long as the flight time. So we selected about 3 runs, so this should take probably something like 10 minutes or 15 minutes to do the processing. For a 1-hour flight it will take approximately 1 hour, and for a 30-minute flight 30 minutes. Okay, this process has finished, and as we can see, the accuracy has been improved from statistically 13 centimeter noise to a 11 centimeter noise level. This is not very representative because in this specific flight there was so much vegetation, so most part of the area is covered by trees, and there's not a really good improvement for the match. This works much better on flat surfaces, on roads, on big concrete areas, on flat areas, where the matching algorithm between the point clouds can be much more improved. Okay, I close this report. And we will not really see a huge difference in the point cloud right now. It's just an overall improvement, which you can later see in the entire point cloud when you inspect the point cloud with some cross sections. So finally, the last step in this tutorial video is how to produce the classification, the ground point and the vegetation point classification. Therefore, we go to this module called terrain, and here we have a limited number of parameters. So let's first start with the kind of terrain we are looking at. Is it a flat terrain here, or is it hilly, or even steep or extreme steep terrain like in the mountains? In this area I would say it's a gently rolling hills environment, and therefore we select hilly. The minimal object height here is the height which we would use as a minimum height for vegetation. Here I actually would like to do something like 20 centimeters. And the maximum object height is the highest tree in the area. I would say this is probably not more than 35 meters. So 35 meters maximum object, 20 centimeters smallest object. Point cloud thickness is an automatic value taken by the software from the overall statistics. And now we are ready to hit the classify button, and this will again take a while. And then we can check the results. Okay, the terrain classification has been successfully completed. As we can see here, now we are looking, we colorize the classification. So the orange points are vegetation or any non-ground points, while the gray points are the ground points. And now if we scroll down here, we can change here between unclassified, ground and other. So for example, we can keep the ground points activated and we hide the other points, and this will show us the non-ground point, the ground points only. And if we now increase the point size a little bit, we can see that we nicely get points in the forest. Well, still kind of enough points. If we zoom in here and we again show the vegetation, so we can see that there is plenty of ground points and non-ground points. What you also can try is you can go back to elevation, so you colorize by elevation, and we can now hide the vegetation or the non-ground points, and still we can now see the ground points, and you can play a little bit with these settings. You can check for the intensity values, and you can see the non-ground points and the ground points. So it's there's lots of tools to visualize the data. So finally, last step is to export the data. And to export data, there's another button here on the left side, the export button. And here you can select whether you want to export a point cloud. So point cloud or a digital model. We will start with the point cloud. You can specify the point cloud format. I would like to export an LAS file, so 1.2 for example, LAS 1.2. We can give it a name, so we call it, let's say, flight 3, and then it will number the runs, and then you have the choice whether you want to export the point classes, which I would recommend you to do. And of course you can also merge the stripes to one point cloud, or you export them separately as single runs. I usually export them as single runs, and later in, for example, in Cloud Compare, I merge them together, because sometimes it's quite nice to have them individually, to clean them up, to inspect them for noise, or inspect them for some objects you want to delete, like cars or whatever. And this is sometimes easier if you operate it, if you process one run by run instead of having the entire point cloud. So once we are happy with that, we press the export button and the point cloud is exported. This again takes a few seconds, and then I would like to show you how to export the terrain model directly out of the YellowScan CloudStation. Okay, export is done. So next we select digital model, and we can do the export as a surface model or as a terrain model. Actually, you would like to have a terrain model and a surface model. I would like to export both of them. We can generate a hill shade. Typically, I would do a unidirectional hill shade, which is the standard one. And then we just, again, click export, and the data will be written to an export folder under the YellowScan main directory. So remember, there was a directory called Flight 3 Tutorial, and below this there's the YellowScan project directory, and inside this directory we will then find an export folder with all the point clouds, with the LAS files, and with the terrain files. So this was the last step. Let me show you the final results. We browse through the right folder. We go to the Flight 3 Tutorial, YellowScan folder, export, and here you can see the 3 LAS files. And we have the DSM and the DTM TIFF file, and of course we have the hill shades. And for example, if you look at the DTM hill shade, you can see this is the hill shade with the holes, and of course we can create a hill shade later with the Cloud Compare software, for example, or with TerraSolid, which is a watertight terrain model without any holes. Okay, now I would like to show you in another short step how to produce a watertight terrain model without any holes. So of course we have some settings here as the pixel size and the maximum hole size. And if I, for example, change the pixel size here to a 1 meter pixel size and the maximum hole size to let's say 70 meters. It will probably create a watertight terrain model without any holes. So let me just export again. Yeah, so now with the 1 meter cell size, it was much quicker than with the 50 centimeters before. And now let's check again. Let's check again the results. So now the terrain model is watertight, so there are no more holes, and we can see that this works quite nice. I hope you enjoyed this short tutorial video. I was recording the video in one go, so it's really uncut, and it's just a short video to help you to get started with your new equipment with the LiDAR Qube 240, and you hopefully find it really easy to process the data with the POSPac software and the YellowScan CloudStation. Okay, hope to see you soon. Have a nice day. Goodbye.